Okay, and we're live. Good afternoon, everyone, distinguished delegates, colleagues, and guests. My name is Jona. I serve as advisor to the Icelandic Minister for Environment, Energy, and Climate. On behalf of the Icelandic government, it's my pleasure and honor to welcome you here today to the Iceland-Chile ICCI Pavilion. So today's side event will focus on one of the most consequential and fast-evolving issues in climate science, the future of the Atlantic Meridional Overturning Circulation, AMOC, we will call it today for simplification. We're fortunate to be joined by leading scientists, experts, and policymakers. And without further ado, I will let Jóhann Páll Jóhannsson, our Icelandic Minister for Environment, Energy, and Climate, open the floor and deliver his opening remarks. Welcome, Jóhann.
Thank you. No way I'm going to wear a jacket. I hope you excuse me. Dear Excellencies, colleagues, there's a fire. Oh, whoa.
They are managing it. Yeah, but let's go. Yeah. Let's go.
Hi, Stefan. Sorry, but we've got a fire in the venue, so we're all going to head out. We'll be in touch via email, okay? Thank you.
Dear colleagues and guests, I'm speaking from the airport after a fire broke out at COP and we had to evacuate and move this event online, but I'm glad that everyone is safe. So, as you know, this event is dedicated to the risk of AMOC collapse and hosted by Iceland. For us, the future of the Atlantic Meridional Overturning Circulation is not an abstract scientific question. It is a matter that touches our national identity as a North Atlantic nation. The ocean shapes our climate, our energy systems, our food security, our infrastructure, and our way of life. And when that system shows signs of stress, it is our duty to pay attention. In August, I was made aware of recent scientific findings on the increased likelihood of an AMOC collapse beyond this century. It is the obligation of politicians to listen to the best available science and act before it is too late. New research has strengthened concern that if global emissions remain high, the likelihood of a major AMOC weakening or collapse later this century rises sharply. And as with other cryosphere tipping elements, the timing is uncertain, but the risk is credible. And the consequences could be profound and long-lasting. As a minister responsible for the environment, energy and climate in Iceland, I cannot disregard findings like this, and hence Iceland took the unprecedented step of bringing the AMOC issue before our National Security Council, the first time we have treated a specific climate tipping risk at that level. We did so with care and deliberation, because the implications of a significant AMOC disruption extend far beyond environmental concern. They reach into food and water security, marine ecosystems, transport, energy systems, financial stability, and overall societal resilience. For Iceland, colder and stormier conditions, stressed fisheries, disruptions to ports and aviation, and potential effects on hydropower and geothermal systems would be deeply felt. And we owe it to our people and to future generations to ask the responsible question: how do we prepare for such a possibility? not because collapse is inevitable, but because ignoring systemic risk is unacceptable. We are therefore taking a precautionary approach and reviewing what additional policies and contingency measures may be necessary for Iceland given the latest scientific findings. And this year, Iceland will publish its first national adaptation plan, focusing on cross-border climate risks and regional vulnerabilities. And we are also preparing a national disaster preparedness policy to be completed in 2028. Within the Nordic Council of Ministers, after climate scientists raised their concerns at the Arctic Circle Assembly in Reykjavik last year, the Nordic Working Group for Climate and Air launched new collaborative efforts to study climate tipping points and their implications for our region. This has importantly encouraged responsible action across the Nordic countries. But preparedness alone will not be enough. The single most important factor determining the stability of systems like the AMOC is the level and duration of global warming. As we stressed earlier in this COP, cryosphere thresholds are not forgiving. Overshooting 1.5 Celsius degrees, even temporarily, increases the risk of irreversible and multi-century impacts. Accelerated sea level rise, destabilized ocean currents, thawing permafrost, collapsing glaciers, so prevention remains our first duty. We must do everything in our power to avert climate tipping points, and this means reducing emissions faster than is currently being done. Iceland is committed to doing its part. We are expanding renewable energy, we are supporting nature-based solutions, restoring ecosystems and advancing innovative technologies such as Carbfix, which mineralizes CO2 permanently underground. We are committed to supporting global adaptation efforts and to ensuring adequate financing for loss and damage where adaptation is no longer possible. But none of us can address climate risks alone. AMOC stability, ice sheet stability, ocean circulation, these are global commons. They require cooperation, shared data, open science and coordinated early warning and preparedness systems. My hope is that together we can move climate tipping risks, including AMOC weakening, from the margins of scientific discussions into the mainstream of global policy and security planning. We can no longer afford to separate climate science from long-term national strategy. We cannot protect our people unless we act with foresight. All of this is why Iceland chose to invite you to this event today, to have a discussion on this challenge. While we still can consider and ponder our next steps, we believe that confronting climate tipping points and the risk they pose openly is not a sign of pessimism or alarmism, but a sign of realism and responsibility. I'm looking forward to today's discussion online. Thank you so much.
Hello, everyone. My name is Stefan Rahmstorf. I am Professor of Physics of the Oceans in Potsdam in Germany. A major risk for society is instability of the Atlantic overturning circulation. And let me briefly explain what that is. We see a schematic on the right-hand side here. It consists of a relatively warm current flowing all the way from the Southern Ocean through the Caribbean into the high northern latitudes, where a lot of heat is given off to the atmosphere, so the water cools and thereby becomes heavy enough to sink down. And it returns as a cold current, shown in blue here, at a depth between 2,000 and 3,000 meters to the south. So that leaves a huge amount of heat behind, about 50 times the total energy use of humanity. It's called the Atlantic Meridional Overturning Circulation, but in short, we call it AMOC. It is often confused with the Gulf Stream because it partly coincides part of the way with the Gulf Stream, but in contrast to the Gulf Stream, which is mainly driven by the winds and will always flow as long as the winds blow. The AMOC is driven by density differences, and that is the reason why it can be quite unstable, as we have seen in the history of the Earth a number of times. And also, the main heat transport comes from the AMOC and not actually from the Gulf Stream per se. Now, if we see in the background here the trend in satellite sea surface temperatures, we see a funny thing there happening in the northern Atlantic, which is called the cold blob. It's actually a region of a cooling trend that has been already going on for many decades, here just seen from the satellite data, which is an indication that the AMOC is bringing less heat into this region, and that's why that actually is the only part of the Earth that has cooled since the 19th century, while the entire rest of the planet has warmed. But there is more to see here. This excessive warming along the North American coast is also an indication that comes with a slowing AMOC. We can test these things with climate models. Here is an example from the Geophysical Fluid Dynamics Laboratory in Princeton, which shows in the colors the sea surface temperatures, and you can nicely see the Gulf Stream in red, warm water coming up from Florida along the American coast, and then starting to meander as it leaves the coast. And in blue, the colder water coming down from the north inshore of the Gulf Stream. With these models, we can perform experiments, and one example of such a model experiment is shown on the left here, and that is a pure breakdown of the AMOC, in this case initiated by adding some fresh water to the North Atlantic, which dilutes the waters there so much that they can't sink down. And the temperature effect of such an AMOC shutdown consists of that kind of cold blob and the warming along the American coast, as you can see here. There's no climate change driven by greenhouse gases in that model experiment. It just shows the pure effect of an AMOC shutdown. Now, if you compare that to the observed change in sea surface temperature, here the global mean sea surface temperature warming has been already divided out of it. So it's a pure, the difference to the global change, and you see that same pattern that is associated with an AMOC breakdown. Don't compare the colors because they're different scales. So on the right-hand side, this certainly doesn't indicate an AMOC shutdown, but it does indicate some amount of weakening. We can also look at this in another model simulation. This is from the GFDL in Princeton, and it's not an AMOC shutdown run. It's a 2 times CO2, so future global warming scenario. But you see that same fingerprint pattern there of an AMOC slowdown. And in the model, of course, we know it's an AMOC slowdown because there we have all the information, what's happening at every grid cell in the model. If we look at the observed trend since the 19th century, based on mainly on shipboard measurements, that is a fuzzy picture, of course, because we don't have shipboard measurements in every spot in the ocean every year since 1870. So there's a certain amount of space-time averaging involved. But I think you can see that basically it shows that same fingerprint pattern of an AMOC slowdown. And that is one of the strong pieces of evidence that this kind of AMOC slowdown is already ongoing, has been ongoing for quite a while, because we don't have direct measurements of that going back further than just 2004 when they have started. And this pattern that we see in the data, we estimate corresponds to about 15% weakening of the AMOC. And here again, that those satellite data that I already showed earlier, which also clearly show that same fingerprint pattern. There's also the possibility to use sediment data from the bottom of the Atlantic to reconstruct the strength of the AMOC. For example, the grain sizes below that deep southward return flow, the so-called North Atlantic deep water. And there's been a number of studies by paleoclimate data study groups that have tried to reconstruct the AMOC going back a millennium and more. And of course, each methodology has uncertainties and can be questioned. The fact that very different methods lead to very similar time evolution makes this quite a robust result. And we see that the AMOC has been stable for many centuries until it has been going into this unprecedented decline over the last 100 years or so. One big problem with this is that we know the AMOC is a system with a tipping point. If it gets too weak, it will become unstable and shut down altogether. And that has been known since 1961, since famous American oceanographer Henry Stommel showed the basic physical principle behind that, which you see in the diagram here. If you start at the point of present climate on that green line, the green lines are the equilibrium strength of the AMOC, and you move towards the right by adding fresh water, which dilutes the North Atlantic Ocean and slows down the AMOC. You can see the AMOC weakens as you move along that green line further to the right, but then this line bends back on itself because there is this tipping point, the so-called Stommel bifurcation point, and basically then it drops off the cliff and it just kind of becomes so unstable that it will shut down altogether. And in fact, that happens in quite a few of the standard global warming scenarios that are calculated and shown in the IPCC reports regularly. These are the CMIP6 models from the latest IPCC report. And it's a selection of those models where the AMOC actually collapses. And so there are more models I'll show you in a second. But you can see that it basically goes into steep decline throughout this century, which agrees with the short bit of observed trend that we have since the year 2004. If we only had these observations, we wouldn't know, is this really climate change or just natural variability? But it does agree with those model simulations that show the AMOC is on the way to shut down there. And for high emissions, all 9 models that have been continued beyond 2100 into the future show that the AMOC shuts down there. But not all models have been continued beyond 2100, so we applied a simple criterion. We believe that if the models have an AMOC that is weaker than 10 Sverdrup, that's 10 million cubic meters per second flow in 2100, then they will almost certainly lead to a full shutdown of the AMOC. And then if we take all these models, all the lines there for low, intermediate, and high emissions, and look at the percentage that is weaker than 10 Sverdrup in 2100, we can estimate the AMOC shutdown risk. And for high emissions, that turns out to be 70%, intermediate emissions 37%, and low emissions 25%. When I first became aware of these results, I was really shocked because I have studied the AMOC stability for almost 35 years now. And for the first 3 decades of that, we considered an AMOC shutdown a low probability but high impact risk. And it was basically accepted that the probability of this happening is less than 10%, but it would still be too big to ignore. But now the probabilities look much higher. And there are also reasons to believe that this is still an underestimate because all of these models I show here do not include the meltwater input from the mass loss of the Greenland ice sheet, which will come on top of that and also contribute to a weakening of the AMOC. Another very concerning thing is the question where the tipping point occurs And the tipping point, it's a kind of point of no return. From then on, the AMOC has been destabilized and will kind of wind down to a completely shut down state, which still takes about 50 to 100 years to fully complete. But the tipping point in some of these models is actually quite close in the future, in the next decade or 2 or 3, as you can see here. We believe that when the deep mixing, the so-called convection in the North Atlantic stops, that is the tipping point, because then there is no more renewal of that deep water. And so that means from then on, just the existing dense water sitting in the North Atlantic will slowly erode away and the AMOC will shut down. And that tipping point where the convection collapses in many of these models is really, as you can see in the bottom panel from 2 examples, quite close. It's in the middle of this century. The impacts of an AMOC shutdown would be very serious. I think many people know about the regional cooling that we would get. No, that's not an ice age, as some media sometimes like to claim, but it is a very serious regional cooling, which also sets up a very strong temperature contrast between the colder Northwest Europe and the warmer Southern Europe. And that temperature contrast, of course, is what drives extreme weather events. So we'd have to expect the kind of extreme weather events that we've never known before if this happens. But there is more. For example, a shift in the tropical rainfall belts. In the purple here are regions that will see less rainfall, and in the green, regions that see more rainfall. And so you can basically see tropical rainfall shifting towards the south onto the equator, whereas in the present climate, it's north of the equator, because the AMOC is the reason why the whole northern hemisphere is actually warmer than the southern hemisphere. And that will end once the AMOC shuts down. And for example, you see big rainfall reductions in India and other parts of Asia, which we've also seen in the Earth history when the AMOC shuts down. So it's not just modeling, it's also the experience of past natural climate changes that make us come to this conclusion, and that can lead to serious drought in parts of the tropics. Another not so widely known impact is that there will be a dynamic sea level change when the AMOC shuts down. That is in addition to the sea level rise that happens from global warming for the global mean, because the seawater expands as it gets warmer and continental ice melts. That's in addition, we can get these dynamic changes, which is simply a redistribution of the ocean water, with sea level rising in the North Atlantic and parts of the South Atlantic, and dropping relative to the global mean sea level in other parts of the ocean. In short, what that means is we can expect between 0.5 meter and 1 meter of additional sea level rise, in addition to the global rise that's already going on. To conclude, many of the standard climate model runs have an AMOC that is on the way to collapse. The tipping point is probably in the next few decades. The collapse risk is reduced by lower emissions, although we can't rule it out. We can't reduce it to anywhere near zero, but we can reduce it a lot. But there is no time to lose, because the tipping point is probably quite close. And if you want to read more about this, this is a free article in the Oceanography magazine that you find online. Thanks very much for listening.
Hello everyone, I'm Kate Fernio and I'm a climate science advisor in the UK Department for Energy Security and Net Zero. I'm very pleased to join distinguished colleagues at this excellent event on AMOC today, organised by Iceland and the ICCI. Before talking about how the UK government is studying risks and possible adaptation to AMOC, I firstly just wanted to comment more broadly on the implications of this event and what it means here in the context of COP30. The risks that we've heard today send a clear message. We need the highest possible ambition to limit warming. And although limiting long-term warming below 1.5 degrees is now unlikely, it remains the right limit, and every fraction of a degree matters to minimise the risks to people and nature from climate change. We know from the evidence that's been presented today that we might have passed or be about to pass thresholds that could commit us to weakening of the AMOC. But our best chance to minimise the risks of crossing these thresholds and others is to minimise the magnitude and duration of overshoot. So to respond to the scale of this issue, COP30 needs to send a really robust signal on countries' continued commitment to action and ambition. On AMOC specifically, and in terms of how well known the risks is, it's something that the UK government is well aware of and takes very seriously. The IPCC found in its 6th assessment report that there's medium confidence that there will not be an abrupt collapse of AMOC before 2100, and this conclusion still stands. But there's a lot more evidence that we have now on AMOC that can be assessed in the 7th assessment report, and the UK is working actively on these areas of uncertainty. It's really positive that the outline of the IPCC's Working Group 1 report has a new Chapter 8 on abrupt changes, low likelihood, high impact events and critical thresholds, including tipping points in the Earth system. This dedicated chapter can be used to bring together all this new evidence on AMOC and really reflects the expansion of that literature base. And in terms of how the UK is contributing to that and the steps that we're taking to study AMOC, we've got programmes through the Met Office Hadley Centre Climate Programme, the Advanced Research and Innovation Agency, and also active projects collaborating across Europe. There are 3 key priority areas of research that we're focusing on to better understand AMOC. One is better understanding the connection between deep mixing in the ocean and AMOC behaviour. Secondly, improving representation of AMOC in climate models. And finally, understanding AMOC change under different warming pathways. We really look forward to the outcome of these projects informing the 7th assessment report and beyond. So in terms of how we manage and adapt to the risk of AMOC weakening, it needs to be considered holistically with all the other risks that the UK is facing due to climate change. So this includes slow onset events, compound and cascading risks, and extreme events. Some of these that we know are happening right now as we speak. The risks from AMOC and other low likelihood, high impact events, abrupt changes, need to be considered within this wider picture, and adaptation actions need to be planned and prioritised accordingly. From an adaptation and risk management perspective, discussion on AMOC and other events that are low likelihood and high impact or abrupt brings into focus that we need to move away from planning just for medium outcomes of climate projections and broaden that to think about reasonable worst case scenarios when we're looking at risk management and adaptation, so that we're considering a broad range of futures and adapting as effectively as possible. Finally, I wanted to make a quick point on communication. I think we need to be really careful about how we communicate AMOC. We know that it's a serious long-term risk, as we've heard today, but also it's not an imminent catastrophe. We don't want the science and AMOC to be spun as a mitigation deterrent, either because of the potential cooling effects it may have, or because people feel hopeless and a bit defeatist in the face of alarmist messaging that can sometimes be picked up in the media. We therefore need to explain the science and uncertainties carefully, be really clear about the timelines of AMOC weakening, which are definitely not well understood by the general public, and be clear about why understanding AMOC and the research we're doing helps us to prepare and adapt. So as a community at the science policy interface, it's really important that we frame this as a call for action and not a cause for despair. Thank you.
Good evening, good afternoon, good morning, wherever you are. My name is Pam Pearson. I'm the director of the AMI Secretariat and the International Crisis for Climate Initiative. Like the other speakers at this event that was interrupted this afternoon by the fire and need to evacuate, I'm recording this in the hours afterwards elsewhere in Belém. But thank you for watching. As we heard from Dr. Rahmstorf, of course, the impacts of a potential AMOC shutdown are extreme and many. One of them is the disturbances of different ocean circulation systems, because the AMOC is very much involved in driving many of these, along with Antarctic bottom water. There are droughts as a potential impact, especially perhaps in the western US and the Sahel. And there is flooding and greater sea level rise, especially along the eastern seaboard of the United States. But most drastically, of course, is an extreme cold that would settle over much of the Northern Hemisphere, particularly over Northwestern Europe, where temperatures may be as low as -15 or -20 degrees Celsius than they are today. And when you think about today being about 1.2 or 3 degrees higher than pre-industrial, that gives a sense of how very cold that would be. At the same time, the Southern Hemisphere would warm more, especially as you see in the lower left around West Antarctica, which is already quite vulnerable at today's levels of warming. And so that might speed up any potential collapse of the ice. And the risk of this shutdown is much lower with low emissions as compared to continuing our high emissions of today. As you heard from the Honorable Minister of Iceland, it's essential then that we really stick to the 1.5 degree goal and begin cutting emissions immediately. So how can we do this in a world where we know that the Paris-aligned global warming pathways that were put together for AR6 are essentially no longer achievable? Those would have had us have peak warming of at most 1.6 degrees and warming below 1.5 degrees by 2100. But these are now essentially out of reach due to the inaction of the past 5 years. So what is possible today? Less than 1.5, almost certainly not possible. Even 1.6, the earlier AR6 pathways, extremely unlikely. But limiting overshoot to 1.6 to 1.7 degrees is achievable. And the next slides are based on groundbreaking work by the Potsdam Institute together with Climate Analytics to look at what we need to do to take ourselves back to 1.5 by end of century. And what this means is that emissions must fall faster, but they are able to catch up with AR6 by the late 2030s, and they actually can reach net zero earlier, mostly because of the large expansion in renewables. And these are essential to drive reaching of net zero and also the post-peak temperature decline. And with these pathways, peak warming is limited to 1.7 degrees, and we can reach perhaps a temperature of 1.2 degrees by end of century with deployment of sustainable CDR. And this is conservatively deployed. This is not magic, it's existing and feasible methods, and it's without the far less feasible and risky geoengineering schemes that have gained a lot of attention recently. Particularly from those wishing to slow polar warming. Those are unnecessary and they're quite dangerous, and they're not really addressing the main problem, which are greenhouse gas emissions. Nevertheless, we will see overshoot of 1.5 degrees for around 40 years as opposed to 30 years in the lowest AR6 emission scenarios, but again, coming potentially even lower than under the AR6 scenarios by following the new highest ambition pathways scenarios. But to achieve that, the global stocktake agreed in Dubai at COP28 is really essential. We need to see complete phase out in the second half of this century and a real emphasis on renewables, wind and solar, starting really today and drastically expanding after 2030. So 1.5 remains not only the right limit, but also an achievable limit, and what is extremely important in lowering the risk of shutdown of the AMOC. We are already seeing devastating consequences. We're seeing other impacts in cryosphere in addition to impacts on ocean currents at both poles, which really do drive the entire ocean circulation system. And we need to keep this benchmark for climate action because there will be a lot of economic benefits and minimizing of risks or slowing, perhaps even halting cryosphere loss that is driving really worldwide impacts. Thank you again to all of the speakers who, despite the fire, were willing to record their planned remarks in the hours after the fire. As a final word, I wanted to note that here during COP30, we have not only seen fire, but floods. The pavilion where this took place, the Cryosphere Pavilion, had standing water at times, as did our friends at the Pacific Pavilion nearby. Increased flooding and fires are two extreme and global potential impacts of AMOC shutdown, as well as continued cryosphere loss should our current emissions continue. You can see this detailed in other events at COP30, as well as the 2025 State of the Cryosphere report. But what we especially can see from AMOC shutdown is that we are driving the Earth system in dangerous ways that we cannot fully predict, with a planet that potentially is in extreme deep freeze in parts of the Northern Hemisphere, and even hotter than projected in the Southern Hemisphere and around Antarctica, which holds 58 meters total sea level rise. There is really no comparison to the current increase in carbon dioxide concentrations in Earth's history, going from the normal level of 280 ppm for a period without an ice age, such as through about 1880, down to 180 ppm during an ice age. We've instead reached 430 ppm several times in 2025, and the ice and ocean currents are responding. This is why we say that there is no negotiating with the melting point of ice. Addressing the root problem of greenhouse gas emissions is the only feasible way to slow and avoid these dangerous developments. The latest AMOC science shows that it's in the direct interest of the global north, not just in vulnerable nations of the global south, to treat this as the emergency it is, with fossil fuel phase-out fully agreed and beginning immediately. This is the COP30 Cryosphere Pavilion, signing off.